Consider the function y is the square root of x squared minus 1. Sketch the curve y is f of x, clearly indicating the coordinate of endpoints. It's a paper with a calculator, so you may just use a calculator to plot a given graph. And it looks like this. Endpoints are when x is 1, y is 0, when x is 2, y is the square root of 3. So it looks like this. And the next question shows that the inverse function of f is given by, states the domain and range of the inverse. You can just find the inverse. To do that, we change x for y for x, hence it becomes x is the square root of y squared minus 1. And we need to solve for this new y, which is the required inverse function. So it becomes x squared plus 1 is equal to y squared, and y is equal to, in general, it may be plus or minus the square root of x squared plus 1, but we know that x for usual function becomes y for the inverse, and we can see that x is positive for f, hence for the inverse y will be also positive, hence we choose plus, so y is square root of x squared plus 1, which is equal to the inverse. And domain and range. Domain for the inverse is the same as range for usual function, and we can see that y values for just a function are in between 0 and root 3, hence it becomes domain for the inverse, so x is greater or equal than 0 and less equal than root 3. And range, y for inverse is the same as x for usual function, hence range for the inverse is y greater or equal than 1 and less or equal than 2. And the next question, the curve is rotated 2 pi about the y-axis to form a solid of revolutions that is used to model a water container. Shows that the volume of water in the container when it is filled to a height of h meters is given by. So we need to find volume of a solid of revolution. Formula is given in a data booklet, and since it is rotated 2 pi about y axis, volume is pi, limits are on y axis, and since it is filled up to some height of h, so limits are from 0 to h inverse squared dx, and it is equal to pi integral 0h inverse squared. It becomes x squared plus 1 dx, can be easily integrated, and it becomes pi x cubed over 3 plus x, and limits 0h, substituting the upper limit, it becomes pi h cubed over 3 plus h minus, and substitute the lower limit, it's just 0, hence it's the required value for volume. And the next, hence determines the maximum volume of the container, and we can see the maximum possible volume, it's when h it is equal to its maximum possible value. So we can see that when h is the square root of 3, we get the maximum volume. H is root 3, we get the max, which is just substituting root 3 for h, pi root 3 over 3 and root 3 cubed plus root 3, and it can be simplified, and it becomes 2 root 3 pi meters cubed, or it's 10.9 to 3 significant figures meters cubed. And the next, at t equals 0, the container is empty, water is then added to the container at a constant rate. So dV dt, rate of change of the volume, is equal to 0.4 meters cubed per second, and it's constant. Find the time it takes to fill the container to its maximum volume. Since rate is constant, time is just volume divided by the rate. So 2 root 3 pi divided by 0.4 is equal to 5 root 3 pi seconds, or 27.2 to 3 significant figures seconds. The next. Find the rate of change of the height of the water when the container is filled to half its maximum volume. So we need a rate of change over the height. So we need dh dt. And to find it, we can differentiate v with respect to t to get dv dt is equal to pi and 1/3 derivative of h cubed with respect to t is equal to 3h squared dh dt plus derivative of h with respect to t is dh dt, and dv dt it's this 0.4, so it becomes 0.4, and we can just solve for dh dt, and hence it becomes dh dt h squared plus 1 is equal to 0.4 over pi, hence dh dt is equal to 0.4 pi h squared plus 1. And we need this rate at specific moment of time when volume is equal to half its maximum volume. It means that when volume is equal to just root 3 pi, it's this divided by 2, and since volume, formula for volume, it's this again, pi 1/3 h cubed plus h, and we need to solve for h, and hence we find the moment of time when it happens. So we need to solve for h, and you can do that with a calculator, and h is 1.18 and so on, and we substitute it here, and hence we get dh dt is equal to 0.4 pi 1.18 by 8 squared plus 1, and it is equal to 0.0531 to 3 significant figures meters per second. Or another way, since we need dh dt, we can consider dh dt, and it is equal to, and since volume is involved, we can do the next. dh dt is equal to dh dt, it's the same. But here we can multiply numerator denominator by dv dv, and hence we get the next. dv dt in numerator and dv dh. It's like operations with fractions. And dv dt it's 0.4, it's the rate of change of the volume, it's constant, and dv dh it's just derivative of the volume but with respect to h, and it's just 1/3 multiplied by 3h plus 1, because it's with respect to h, and when it's derivative with respect to t, then dh dt arises according to the chain rule. So we get 1/3 times 3h squared plus 1, and we can see that we get the same result. and end pi here, pi in front. Yes, it's the same result. And also we need to find h when volume is equal to half its maximum value. To find this h, substitute and calculate dh dt. And that's all for this question.